So here's the video for change of concentration with time, which I am recording on Saturday because I really think that we're probably not going to have school on Monday, but we'll see what happens. Um, anyway, so you can watch this in case we don't have school Monday. So I guess enjoy your snow day. Sorry for making you work on your snow day. So how concentration changes with time. Now just to kind of back up for a second here, we were talking about concentration and rate. So if we change the concentration, how does that affect the rate? That was kind of what we were focused on in 14.2 and 14.3. Now what we're going to talk about is how concentration changes over time. And you can actually, not in just the same way, but in a similar way, you could figure out the overall order of the reaction based on looking at each of the different reactants and figuring out if we change the concentration of this reactant, how does that affect the rate? Okay, so we did some example problems here, very similar to this one, where you double the concentration of one of the reactants and see how that affects the rate, and then you double the concentration of the other reactant, see how that affects the rate, while holding the other ones constant. So then you can end up writing a rate law, and the rate law for this one ends up being rate equals K times A squared. B ends up not being in the rate law at all because it doesn't matter what concentration of B you have, the rate is going to happen the same. Because if you look at the first two experiments here, we double the concentration of B from experiment 1 to experiment 2, didn't do anything to A, and the rate didn't change at all. So the concentration of B has nothing to do with the overall rate of the reaction. So it doesn't go in the rate law. Okay, but if we wanted to know the overall order of this particular reaction, it would be 2. Okay, the overall order would be 2. Now it would be second order with respect to A as well, but the overall order here is it's a second order reaction. So we can figure it out by looking at what happens to the concentration, what happens to the rate when we change the concentration of one of the reactants. There's another way to go about it. We can actually figure out how does the concentration of the reactant or reactants change with time, okay? And so you can figure out, is this first order with respect to a certain reactant? Is it second order? Is it zero order? Okay, I need to remember to talk about zero order because it's not in these notes, but zero order is easy. In fact, let's cover zero order first, just so I don't forget to do it. So with a zero order reaction, and our strategy on all of these is we're going to measure the concentration over a certain amount of time, and we're going to see what happens. With a first order reaction, the concentration has no bearing on the rate whatsoever. Okay, so if I have, maybe reactant A, and I do a graph of reactant A, the concentration of A over time, it's just going to be a straight line down, okay? And the reason for that is because over time the concentration is, going steadily down, and the fact that the concentration is decreasing doesn't decrease the rate at all. So the concentration of A is going to decrease at a steady rate, at a constant rate, the entire time, okay? Now, for a first order reaction, so that's a zero order reaction. So actually, if you see a graph like that, where it's concentration versus time and it's a straight line graph, that tells you that it's zero order with respect to A, okay? So in other words, because the concentration of A is just decreasing steadily over time, it must have no bearing on the reaction rate. So that's a zero order reaction, okay? Now a first order reaction, we've already gotten this equation. This equation we've talked about. Have we talked about this equation? Yeah, we have. Okay, so we haven't talked about it all together like this, but if you want to find the rate, you take the opposite, the negative of the change in A, the change in the concentration of A over time, okay? That's also equal to K times A to the first power, because in a first order reaction, you're only going to have that one thing, and it's going to be raised to the power of 1. If it was raised to the second power, then it would be a second order reaction, okay? So we can kind of make those things equal to one another, all right? Now, the benefit of doing this, Now that you have these two things equal to one another, you can kind of cut the rate out of the equation for now and not worry so much about that. And now we've got an equation that relates the rate constant to our change in time, and we can really focus on that. But you have to use calculus for this. Okay, so we're not going to get into all the calculus, but if you skip forward a couple of slides here, if you were to graph a first-order reaction, okay, this is concentration or pressure, doesn't really matter which, we're talking about here. Pressure over time, concentration over time, it's not going to give you a straight line. It's going to give you a curve like this. The reason for that is the rate of the reaction is going to slow down as the concentration changes. So you have less of the reactant. That's actually going to cause the reaction to happen slower, okay? And so this is not a zero order, this is a first order reaction, and in first order reactions, the concentration does affect the rate of the reaction. So that's going to actually slow it down. Now, if we want to straighten this out, if you have a curve like this, and you want to straighten it into a straight line, one thing that you can do is you can natural log both sides of the equation, okay? And again, I'm not too worried about showing you the derivation of this because they've specifically said that derivations are not as necessary in the new AP curriculum as they kind of used to be. Or honestly, I had never seen them do this, test this derivation anyway. But they have specifically said now that you don't need to worry about a derivation like this, okay? They actually give you this equation on your equation sheet. They give it to you in just a slightly different form. The form that they give you is, okay, it didn't go away. This one right here, okay? So that's what it looks like on your equation sheet. Now, it's very easy to rearrange that to make it look like this. All you have to do is put the natural log of the AT on the opposite side of the natural log of the A0, okay? And then you just kind of have to know what AT and A0 actually mean, okay? AT basically stands for, well, let's talk about A0 first. That's the concentration of A at time 0. Okay, so the very beginning of the reaction, that's the concentration that you start with as the reaction first starts. And then AT is the concentration at whatever time you're measuring. So maybe that's 20 seconds or 40 seconds or whatever it is, okay? That's your AT. So that's what AT and A0 mean. Now the K here is the rate constant, which we talked about on Friday when we were talking about how to write the rate law. You've got to put that rate constant value in there. And then, so this is the rate constant. And then the T is just time. Typically measured in seconds. Not always, but that's typically the unit that we're going to use. Okay? So the idea here, go back to my full screen. The idea here that is, rather ingenious, I think, is that if we rearrange the equation this way, then it looks like a y equals mx plus b equation, okay? And so what you can do, if you graph the natural log of pressure or the natural log of concentration versus time, then what you're going to end up with is a straight line, and your slope is going to be your negative k value, okay? Your rate constant can't be a negative number, all right? So you've got negative k here. Notice your slope here it's sloping downwards. So that's going to be a negative slope, but this negative right here in front of it takes care of that. At the opposite of a negative, it's going to give you a positive, so then you'll have a positive k, positive rate constant. But that's actually a way that you can figure out the rate constant because that's your slope. So basically, we're graphing this as our y value. We're graphing this as our x value. The natural log of A0, that would be your y-intercept. That would be your initial natural log of your concentration here. And then your slope is k. So kind of a handy form. That's why I like that form of the equation a little bit better than the one that they give you on the AP exam. But the typical kind of question you'll get on the AP exam, well, in the past it's been more kind of plug and chug. So you plug in values for these and solve for one of the variables. But I could see them putting a graph question on this new exam because they're so they're emphasizing pictures a lot more and graphs and being able to analyze graphs and that sort of thing. So I think it's important to know what this is actually telling you. Okay, so for a first order reaction, now notice on the equation sheet they don't actually label this as a first order, but in the kinetics section it's the one that comes first. Okay, so it kind of makes sense that's a first order. The second equation here is for a second order reaction, so that's kind of easy to remember. And then the one at the bottom here is a half-life equation, so that's kind of a little bit different. But you can keep those two separate by remembering that they put the first order reaction equation first and then the second order equation second. Kind of interrupted my train of thought there. Let's see. So that's kind of the idea. Let me go back and see if there's anything we really need to talk about here. No, I don't think we need to do that example problem yet. So I just wanted to show you the graph of that, okay? So what this means, basically, a kind of question that they would commonly give you on the AP exam before is they might give you a question like this, where they give you, you know, a couple of graphs. Concentration of A versus time. And then they might give you like a natural log of the concentration of A versus time. And then they'll ask you which one of these graphs correctly represents the graph of a first order reaction. Okay, so then you would say, oh, well, it's the one with the natural log in it. That's the one that's going to give me a straight line for a first order graph. Okay, so the graph on the left here that I drew would be for a zero order reaction. All right. So that's zero order and first order. What about second order? Second order, the equation looks like this. 1 over AT equals KT plus 1 over A0. Okay? And that's going to give you a straight line for a second order reaction. Okay? And again, don't worry too much about the derivation of that. That equation is on your equation sheet as well. Just, again, in a little bit different form. But the reason that they're giving you this form is because, again, it looks like y equals mx plus b. So if you plot 1 over the concentration versus time, your x value, then you would get a straight line graph with your slope being the rate constant, the k. All right? So that one would look like this. Now notice, they're showing you here, if you tried to plot this one with using the natural log of the concentration versus time, it's not going to give you a straight line graph. Okay? For a second order reaction, the only way you can get a straight line graph is if you take 1 over the concentration of the reactant versus time. Okay? Now also notice this one has a positive slope. Okay? And the reason for that is as the reaction continues, the concentration is going to decrease over time, right? But if you're taking the inverse of the concentration, so for example, let's say if we start with 2 molar, okay, 1 over 2 molar, and then later on in the reaction we end up with 1 over 1 molar, obviously, you know, your numbers are actually getting bigger here, okay, because you're taking the inverse of the concentration. So that's why on this graph you end up with a positive slope. But it is still a straight line, okay? And that's why, notice there's no negative in front of the k on this one. There doesn't need to be because you have a positive slope, so your rate constant is going to end up being positive. So again, you know, they might give you all 3 graphs, and they might say, here are 3 graphs for a reaction. They give you the concentration of A versus time. They give you the natural log of A versus time. Sorry, I don't have a lot of room for this. And then they give you 1 over the concentration versus time. And the concentration versus time looks like this. The natural log of the concentration versus time looks like this. And then 1 over the concentration versus time, that's supposed to be a straight line, sorry. Looks like that, okay? And then they ask you, is this a first order, zero order, first order, or second order reaction? And your answer would be this is a second order because the second order graph is the one that gives a straight line. Okay? So pretty simple questions I think that you'll have to answer about the zero, first, and second order reactions. following data was obtained for, let's see if we need to talk about this at all. Well, what's the question? Is the reaction first or second order? Okay, so this is a little tricky. What you would actually have to do on this one, and I don't think they're going to give you one like this on the AP exam, but you would actually have to graph these things, okay, and in two different ways and see which one of the graphs gives you a straight line. Because they're just giving you time and concentration data, okay? Now, if they were giving you concentration and rate data, then you could, you could figure it out the way that we figured it out on Friday, where you're basically just writing the rate law for the reaction based on what happens to the rate when you double the concentration. But since they're only giving you what the concentration is doing over time, then what you're going to have to do is make two graphs, okay? One of your graphs, the graph that would correspond to a first-order reaction would be the natural log of your concentration versus time. And I guess actually I didn't need to write A for this one. It's NO2 is the species we're working with here. Okay, so natural log of the NO2 concentration over time. So you'd have to find the natural log of all these numbers and then graph that versus time, okay, and then see if that gives you a straight line or not. If it does, we're dealing with a first-order reaction. If it doesn't, probably dealing with a second order, but it would be a good idea to check just to make sure. For a second-order reaction, if you graph 1 over the concentration versus time, then that should give you a straight line. So we would take 1 over each of these concentrations, graph that versus time, and if that gives you a straight line going up, then we're talking about a second-order reaction, okay? Now, it should only be one or the other. One of the graphs should give you a straight line, the other one should not, and that would help you to answer the question whether it's a first order or second order, okay? I like the question. I don't think you're going to see anything probably like that on the AP exam. All right, last thing we need to talk about here is half-life. Half-life is how long it takes for the concentration to drop to half its original value. Now, where you're going to see half-life often is with nuclear equations. They took nuclear out of the curriculum. We would have already talked about half-life this year if they hadn't. But it's a pretty simple concept. Basically, it's just, if you have 100 grams of a radioactive sample, let's say. It doesn't have to be radioactive, but that's just a common example for half-life. If you have 100 grams of a radioactive sample, how long does it take for that 100 grams to decay and become 50 grams? Okay? Or really in any reaction, if you have 100 grams of something, how long does it take to go down to 50 grams? If you have a concentration in a solution of 2 molar, how long does it take it to drop to 1 molar? Okay, so basically the time for half of the original reactant to be converted into a product. Okay, so that the concentration of the reactant is now dropped to half its original value. All right, now this is something new on the equation sheet, and I'm glad because they said that they were, trying to put less of an emphasis on derivation, and this is kind of proof of that. Here's your half-life equation for a first-order reaction, okay? I don't think that you're going to need to know the half-life equation for a second-order reaction. But I'm going to show you how to do it just in case, just so that I can cover my bases here. And then I'm also going to show you how the first-order equation is derived, just so you can see it, because I think it's a little bit interesting. Even if you didn't have that half-life equation, you could figure it out just by plugging back into your original first-order equation that they give you on the equation sheet. So the equation is natural log of a at time t minus the natural log of a at time 0 equals negative kt. All right? So let's say we start with that. You know what? I'll just do it on the screen so that I have it right here. So the natural log of, well, I need to rewrite what they already have written. The natural log of a at time t minus the natural log of a at time 0 equals negative kt. Okay? This equation right here. For half-life, we need to solve for the t. Okay? And this time that we're solving for is the time it takes for us to end up with half of our original concentration. Okay? Now, what you can do here, and if you're in pre-calc math analysis right now, then you might have already learned this. But when you take a natural log minus a natural log, so if you have natural log of x minus the natural log of y, for example, you can rearrange that to be the natural log of x over y. You can kind of combine the two terms. Okay, so that's what we're going to do here. So you've got the natural log of a at times t minus the natural log of a at times 0. So we can rearrange that to be the natural log of a at times t over a at times 0, and that's equal to negative kt. All right? Now, we can actually relate the concentration of a at time t to the concentration of a at time 0 for solving for half-life. Because in a half-life situation, then our final concentration has dropped to 1/2 of the original concentration, right? So a really simple way to do this is just, plug in some numbers, right? Let's say that our original concentration was 2 for our A0. That would make our final concentration 1. So then what we're going to end up with, no matter what numbers we plug in here, we're going to end up with the natural log of 1/2, okay? And that's equal to negative kt. You can actually plug natural log of 1/2 into your calculator, and it's going to give you the number 0.693, negative 0.693, okay? So you can just actually solve that. And then, oops, I got my negative sign here. Then if you divide both sides by negative k so that you get t all by itself, because we're trying to solve for t here, then what you end up with is the equation they give you right here. T 1/2 is equal to 0.693 over k. All right, so that's how they derive that half-life equation, just in case you're interested. But you don't need to derive it because they've given it to you this year. I had to teach that to my students last year because they didn't actually provide that equation for them. So, so there's that. I've showed it to you just in case. Now, let's say just weird scenario here. They ask you some sort of half-life question about a second-order reaction. I really don't think that's going to happen, but just in case they do, this is our second-order equation, and you just basically do the exact same thing. Okay? So let's see here. Let's say that, again, just plugging in my numbers that I had before. AT, let's say that is 1, A0 was 2, okay? So basically what I'm doing here is I'm taking, well, no, let's be a little more careful here. Write it more generally than that. So on this one, I can say basically that, I don't know how I'm going to do this. Now I'm stuck on this one. 1 over, let's call this 1/2, yeah, there we go, 1/2 A0 minus 1 over A0 is equal to KT. Okay, so this time we won't plug in actual numbers. If I rearrange this first thing here, then I'm going to end up with 2 over A0 minus 1 over A0 is equal to KT. Okay? So you take the 2 minus 1 and you end up with, I'll come up here and do it, 1 over A0 is equal to KT. And then if I want to rearrange to solve for t, I divide both sides by k, so then I end up with 1 over k times A0 is equal to t. Okay, so if you ever needed to know the half-life equation for second order, you can just rearrange it that way, and that would give it to you. Now, you don't really need to know that because if they ask you about a half-life on a second order reaction, then what you can do is just pick some numbers here, right? So if they give you the rate constant, which they would have to do on this one, for the second order reaction, then just plug in a couple of concentrations. Plug in 50 here, plug in 100 here. If you've got your K, then you can solve for T at that point, okay? So just, you can always do that as well. All right, so that's that as far as half-life is concerned. I think that's pretty much all we need to talk about with the change in concentration versus time. Okay, one thing to notice here, I guess, if we look back at the first order half-life equation right here, notice concentration is not in the equation at all. So the half-life of a first order reaction does not depend on concentration. All right. Now, all nuclear reactions are first-order reactions. Okay, that might be something to write down. All nuclear reactions, all nuclear decay, I should say, is first-order. The half-life is first order. Okay, so what that means is, basically, if you start with 100 grams of your radioactive sample, after one half-life, it will be 50 grams. After two half-lives, it'll be 25 grams, you know, and so on and so forth. But the half-lives are going to be exactly the same. So if the first half-life is 2 years, the second half-life will also be 2 years. The fact that we now only have 50 grams going down to 25 grams, that doesn't affect the half-life at all. The half-life will stay the same every time. Okay? So that's for a first-order reaction. Now for a second-order, if you notice, the second-order equation still had the concentration in there, so the concentration does affect the half-life of the reaction for a second order. Okay? But first order is what we're typically going to focus on, and for any first-order reaction, the half-life is not affected by the concentration. Okay? Is there anything else we need to talk about here? Okay, this is a good example of one of those types of equations, or one of those types of questions that you might get. Okay? So they might give you three graphs like this and say, is this a zero-order, first-order, or second-order graph? Okay? And so this first one here is concentration versus time. If that was a straight line, then we would have a zero order. The second one is natural log of concentration versus time. If that's a straight line, then it's a first order. And then the last one here, the one over the concentration, that's going to be, if it's a straight line there, then it's a second order. So obviously the straight line is this one in the middle, so this is a first order reaction. Okay? I think that's pretty much it. I think. Determine the order of the reaction with respect to A. What is the rate law for this reaction? Okay, so we could write a rate law, since we know that this reaction is just A to B right here. So the only reactant we have is A. So if this is a first order reaction, then it must be first order with respect to A. So the rate law for this thing would be rate equals K times the concentration of A. Okay? If it ended up being a second order reaction, then the rate law would be rate equals K times A squared, right? And if it had been a zero order reaction, then we wouldn't have put the concentration of A in the reaction at all. It would have just been rate is equal to K, the rate constant, because the concentration doesn't affect the rate in a zero order reaction. Okay? And then the rate constant for this reaction, including units. What you'd have to do on this is actually read some of the numbers off of here, and you could figure that out. Okay, so, or actually, probably the easiest way to do this, sorry, is not to plug in numbers, but to figure out the slope of the equation, because K equals negative slope. So once you figure out the slope of that line, that would give you your K, and then we'd have to figure out the units. But the units for any first order are going to be the same, because remember, if you've got a rate law like this, well, rate is typically measured in molarity per second, and that's going to be equal to K times your concentration of A, which is going to be measured in molarity. So divide both sides by M, and your rate constant is going to be seconds to the negative 1, or 1 over seconds. Okay, so you just find the slope. Your units would be seconds to the negative 1. And that's the kind of thing that you're going to get with the concentration versus time. Okay, that's it for that one. Sorry, I know it was long. And it's still going. There we go.